So I feel the next test.
All right, differential equation. A differential equation is just an equation that involves derivatives. Avery, Lainey, Lauren, everybody's not here. Oh, so good. College. So, but here's what's going to happen. These equations are going to involve I realized that afterwards because Robert came up and said, "Is this the one where I do like the B minus A thing?" And I went, "Oh," or somebody did. I thought it was Robert. I forgot to put that on the test. I forgot to put that on the test.
I was gonna say Brian, I did it on the test.
This is where we're going to get into the indefinite integral a little bit more than what we did before. But all we're doing here is we've got this equation that's got a derivative already in it. In other words, the derivative has already been found. We're going to find that what we call the solutions to this, and to do that, we're just going to solve it for y. This says solve for y, but I don't see a y. So what am I going to do? That's exactly what I'm going to do. I'm going to take out that dy dx, but to do that, I need to kind of undo it, right? How can I undo dy dx? The antiderivative, you're exactly right. Joyce will lead you in the right direction. The integral, the antiderivative, right? The integral, you take the antiderivative to do the integral. All right, so this would give me y equals, and now I do the antiderivative of each piece. What's the antiderivative of secant squared? Secant.
No, it's not that. It's tangent.
It's just tangent. Yeah, derivative of tangent is secant squared. So the antiderivative of secant squared is tan. Did you? Sorry. Everybody was saying something different. What's the antiderivative of 2x? X squared. Oh my goodness, y'all. What's the antiderivative of 5? 5x. And now I need to do plus c on the end. Don't forget that plus c. The difference this time is because I've got what we call an indefinite integral. That's exactly right. Indefinite integrals always get c. There are no bounds. No a and b. Right? I'm not going from something to something else. If I was, I could just stop here and plug in from whatever to whatever, but I'm not, so I have to do a plus c. This is really easy today, I think, anyway. It's just antiderivatives with a plus c. That's all we end up with. That's how we're starting differential equations. Well, let's make it a little bit harder because, and I got to show you slope fields. This is number, I'm going to jump to your homework because it's easier for me to just grab a piece of homework. I'm going to jump to number 8 on your homework. Ugh. Cosine t, e to the sine t. Now, here's where I know we're gonna have to just step here for just a second because this is where we have to think through our chain rule when you think about antiderivative. Okay. Whenever we get right before the AP, or whenever we start getting into review, I've got a couple page document that I'll give you, and then I've got a 1 page sheet that condenses everything you have to know by memory, everything you need to memorize for the exam. No, get nothing. Calculator on half of it. All right, let me show you how I reason through this. Okay, I do what we call use substitution. If I take the integral on both sides, I know that y is equaling the integral of cosine t to the sine t. Yes? Okay. But I don't know the antiderivative of cosine t e to the sine t. You agree with that? So here's what I start reading. Well, maybe we shouldn't. Maybe we should just read. Tell me what you see. Tell me what you see. Well, because I haven't found the antiderivative yet. So as you find this antiderivative, how am I going to reason through what that antiderivative actually is? Okay, so what's the antiderivative of sine or cosine? The antiderivative of sine is negative cosine. The antiderivative of cosine is sine. Neither one of those of which, you see what I'm saying? How am I going to find an antiderivative so that if I take the derivative, I end back up where I started? Right? That's what I got to think about. Okay. Think about chain. Think about your chain rule here. Whenever you take a derivative, right? If I had, let's say, just because I see an e in here, let's say I have e to the x squared. What's the derivative of e to the x squared? E to the x squared times 2x. Where did that 2x come from? The x squared. That's the derivative of the x squared, right? Do you see where I'm going with this? Something's happened here in taking the derivative that's caused me to have this extra piece. Can you see it? It did change. What could possibly I have started with that whenever I took the derivative, I ended up with e to the sine t times cosine t? What's the derivative of that? You're getting close. The derivative of this is e. Now look, right? But it's multiplication, so it doesn't matter. So what is the antiderivative of this? If cosine's in the exponent, I would get e to the cosine x times negative sine x. Right? And that's not what I have here. Well, because there's a use substitution, but if I get into that now, I'm really going to lose you. Most of these you can reason through, is why I'm trying to get you to.
No, I don't.
All right.
Yeah, just tell us the answer.
Okay, so the answer, well, we just did, right? The answer is going to be e to the sine x, or e to the sine t, and then plus my constant.
Okay. They just cancel out.
Okay, look at this and take. Okay. Right, you have to think about the chain because the derivative of e to the x and the antiderivative of e to the x is just e to the x. But you got to chain what's there. So if I take derivative, if I were to do this and come here and do this, it would be derivative of y is e to the sine x, but then I'd have to chain it times cosine x. Derivative of a constant is 0, which puts me back up where I started, which was what I wanted to check to make sure.
Oh, all right, that makes sense. Because cosine t is the derivative of sine. You're fine.
Yes.
Okay.
Let me show you u. Let me show you with the u because y'all are looking at me like
that we should have done that in the first place. That part I actually.
That's the derivative.
No, I know, but you can go backwards. I don't know. Okay, now I think it's starting to click.
Students generally will see this before they understand the u substitution. Is why I showed you this first. But sometimes, all right, let me show you the u just in case you're a u person right now, okay? You'll get to where you have to do u, yeah. Let me show you this. If I want to do the integral of, what was it again? Cosine t e to the sine t. Okay. U substitution. What I do is I let u be some function that's going to help me somewhere. In other words, I know what the antiderivative and the derivative of e to the blah looks like, right? So I think I'll let that blah be u. And it needs to be a function. It needs to be something that you could easily substitute within here. And what happens is you take the derivative of your u. Okay, so this is where I got my u. Now I'm going to take the derivative of my u. Well, the derivative of my u, what's the derivative of sine t? That's antiderivative. Cosine t, right? So since I have both the function I chose and its derivative inside my integral, I can use both of these and rewrite here and say, well, this is the same thing as e to the u. And actually, remember, whenever I take a derivative, I need to follow it with dt, right? Because I don't know what t is. And then this together makes du. Can you now find the antiderivative of e to the u? What's the antiderivative? E to the u. E to the u plus c. Now I just go back in and sub in what I had for u to start with. Better? It's the same, right? It is. It is.
But I mean,
Let's do another one. Either way you want. Maybe we want these parts over. But y'all, I felt like maybe we should wait on the substitution.
let's wait.
No, we already did it now.
Oh. Well, now we can wait on something else.
First thing I want you to do is solve the differential equation. Then we're going to go back and we're going to do something else with it. Would I need to do a u sub here? But even if I wanted to, there's two pieces that are split up with addition and subtraction. The only time I have an issue is whenever I've got that multiplication like that, right? And I've got more than one function in there being multiplied. But here, this is a straightforward, pretty easy problem, right? Mark's like, okay. Y'all remember the plus thing? Find the particular solution to the equation. This is the solution. This is my general solution. Find the particular solution when x equals 0 and y equals 3. It's just a plug-in. I need to plug it in and solve for what? C is 3. Tan 0.
Oh, my bad. What, bro? You act like I know what the unit is. Oh.
Good. These are so hard sometimes. Okay. You just write the equation instead of C. I'm going to show you slope fields just because they're so easy. It's a breath of fresh air, so it's a fun. Everybody loves slope fields because they're so easy. If you hate it, blame me. In fact, if you happen to get, that took a minute to register. That's nice. If you happen to get an AP exam that has a slope field question on it, praise the Lord, because it's an easy question. It doesn't happen often, but it does happen. Every few years or so, they'll throw you a slope field question on there, and it's nice. If it's gonna make me mad, don't even tell me. Okay. I mean, you'll see. Okay, first of all, they don't even release the multiple choice each year, so how does she know that? Let me just say this: when you leave this class and you pass, whether you choose to apply your credit or not, because you'll pass and you'll get credit for Calc 1, right? Even if you go straight into Calculus 2, you will still know everything they're talking about when you get in there. You will have that much knowledge from this class. Wow. I'm telling you. Well, a lot. Believe it or not, and I think this was the year that Ella and Corbin and all of those. I don't remember what year that was.
Apply it or not, whether we apply it or not. Application and knowledge.
Here's what a slope field does. A slope field graphs the slope at various points. Remember, this means slope because that's derivative, right? I want you to think about a coordinate plane. And really, you should really start praying now that they give you one of these that you have to draw out because they're so easy. All right, here's what you do. You think about the points where you are, and generally they'll give you like a 3x3 that you would have to calculate out, that you would have to sketch. For example, here is, let's start 1, 1 actually. At the point 1, 1, what is the slope? Oh yeah, slope field, sorry. Well, at 1, 1, I'm plugging in the slope equation, right? So 2 times 1 minus 1 is still 1, right? So what I'm going to do is I'm going to sketch a little line that has a slope of about 1. Just a little piece of a line. Like, yeah, you're just doing a little, like, just a little, yeah, the slope at 1, 1 is 1. What's the slope at 0, 0? Is that horizontal or vertical? Slope of 0, right. Right, and I could do all of these points this way. How about at 0, 1? What's the slope at 0, 1? Negative 1. So at this point, I've got a negative 1 slope. How about at negative 1, 0? Negative 2. So it needs to be steeper than this, right? And so when you're done, you end up with all these little lines. Let's see what happens at 2, 1. 4 minus 1, 3. So I'm getting steeper. And so these should be getting increasingly steeper, and they should start going towards a vertical line, right? And same with these as I start moving across. Right. Let's do some more down here. Huh? You're putting them at the point. Let me show you what a full-fledged slope field looks like. Your calculator will actually graph a slope field too.
But what is
This tells us a lot about, because remember that the solution to a differential equation has an infinite number of solutions, right? Do you understand why? Why? The C. It's the plus C. It's that constant on the end that gives you an infinite number of solutions, right? This is every solution to the differential equation.
so this is every copy.
Right. That's exactly right. So
we're basically
no, this is in your book. This is one that it says if.
holy cow. That's kind of cool. That's like a brain.
Yeah. So you see the blue dot? It says if that dot is on your graph, what is a possible solution to look like if that's one particular? Remember, we only need one particular solution to find the actual curve or the actual graph. Then we can plug it in and find C. Well, if that one point right there is on your graph, then what does that particular solution look like? Kind of.
What is that?
Let me show you one that I've sketched out. Look at this one. See how it kind of follows along, because that's that one solution. But depending on where that blue dot was, if that blue dot was way down here, it would shift my graph here. Here's another.
What is the blue dot? Like, how do you?
It says match the differential equation with the appropriate slope field to sketch the graph of the particular solution through the point or whatever. So they give you these. They give you these differential equations. Which one matches? And then I was showing whenever we were doing it what that graph would actually look like. You don't have to do it. Just do it right here. I'm telling you, when you dig in, it'll be fun. Here's one that doesn't have. It's kind of, they're connected instead of being so individual slopes, so disconnected, right? So once they're smooth and connected, but you see how the C is changing it. Depending on what the C is depending on which graph you get. but slope field wise, you get them all. It's really cool. It's fun. It's fun. All right, that's all I got for you. I told you today was easy. Yeah, I've worked.